Let us come back to the crack problem that we had handled earlier. In the crack problem, we had used the fact that tractions along these paths where there are no cracks, the traction is continuous, and based on that idea, we uh, we derived a function, new analytic function theta z, which we used in place of omega z. Then looking at the tractions on the top surface of the cracks and at the bottom surface of the cracks, we could reduce the problem to these two equations on the crack faces. On each of the crack faces, if the tractions are F1 and G1 and F2 and G2 on the lower surface, then these two are the equations at the crack faces. These are the boundary conditions at the crack faces. And then adding and subtracting them, we got two Hilbert problems. This is the first Hilbert problem in theta, and this is the second Hilbert problem in 2 omega prime minus theta prime. So these are the two Hilbert problems that we have, which we can solve in order to get theta and omega as functions of z anywhere on the plane. So we will not do this problem in its totality. We will take a subset of this problem, a simpler subset of this problem, which is actually a famous problem that was solved at the beginning of fracture mechanics, beginning of the development of fracture mechanics, and this is a classical problem called the Griffiths problem. So this is called the Griffiths problem. This is an infinite plate, and here is a crack, a single crack running from minus A to plus A. So we are traversing this way. So our first point, beginning point for the crack is minus A, and the end point is plus A. So this is our plus side, we call it S plus, and this is our minus side, we call it S minus. So this is the problem. The crack itself is subjected to tractions on its face. There are no remote loading, so stresses all die down as all stresses sigma ij, they die down as mod z tends to infinity, and the crack itself is being opened by tractions applied on its faces. So on the upper face, the tractions are P minus IQ, P and Q being constants, not functions of. So constant tractions are applied, constant normal tractions are applied. P is the normal traction that is applied on the faces, and then constant shear tractions, Q is the shear traction in the direction of X, that are applied on the top faces. On the lower faces, minus P plus IQ is applied, and they are equal and opposite. So P is opposite to minus P, and minus Q is opposite to plus Q. So they cancel out. So if you now look at the two Hilbert problems that we had, the first Hilbert problem, when there are equal and opposite tractions acting on the upper and lower faces of the crack, the first Hilbert problem reduces to a homogeneous Hilbert problem. The right hand side becomes equal to 0, whereas the second Hilbert problem remains an inhomogeneous Hilbert problem, but the right hand side is now minus 2p plus iq, where p and q are constants. The tractions applied are constant uniform tractions. They do not vary with x. So constant tractions are applied, and you get a constant term on the right hand side. So this is the situation. So this is the homogeneous Hilbert problem, just like we obtained in the case of the punch. And we know that the solution to this is xz times pz, where xz is the Flamel integral, and pz is a polynomial. Now, for this homogeneous Hilbert problem in theta prime z, the solution is this. Why? Because we have xz equal to z plus a to the power minus gamma, and z minus a to the power gamma minus 1. In this case, gamma turns out to be equal to 0. So this is 0. It turns out to be 0 because this quantity beta, remember in Hilbert problem you have phi t minus beta phi plus t minus beta phi minus t equal to 0. This beta in this case is equal to 1. So beta equal to 1 in this case, which implies that gamma is equal to 0 in this case. So for the first Hilbert problem, gamma is equal to 0, and then if you apply gamma equal to 0, this is 0, so this becomes 1, and you have this is equal to minus 1, so you get a Flemmel's function equal to z minus a. That is what you have got, and here is the unknown polynomial. Now, for no remote loads applied, then stresses should all go to 0, and theta prime z should also go to 0 as mod z goes to 0, and that can happen only if pz is equal to 0. Pz is identically equal to 0. If pz is equal to 0, pz, remember, is a polynomial in z, so for it to be 0, for it to go to 0 as z tends to infinity, pz has to be identically equal to 0. So therefore, theta prime z is out of the picture. Theta prime z is identically equal to 0, must tend to 0, and we are left with the inhomogeneous Hilbert problem. We are left with this problem, which is an inhomogeneous Hilbert problem. The solution to this problem is also known to us. So this is the solution. If you look at the Hilbert problem, inhomogeneous Hilbert problem solution, this here you have xz is your Flemmel's function. So you have the pz xz here, and uh, this is the thing that you need to evaluate between minus a and a, minus a and a being the domain of the crack, being the length of the crack. So over the length of the crack, where you have jumps in quantities, across which you have jumps in quantities, you have to evaluate this integral, multiply with xz by 2 pi I, and then pz xz will give you capital omega prime z. Okay, now in this case, let us find the nature of the Flemmel's function. So there's a plus here. So beta is equal to minus 1 in this case. Beta is equal to minus 1 in this case, and we know that beta is equal to e to the power 2 pi I gamma. E to the power 2 pi I gamma, that's your beta, and this beta is equal to minus 1. So when is beta minus 1? So so you have e to the power minus I pi by 2 equal to cos pi by 2 plus I sin pi by 2. Sorry, and this is not it. So you have cos e to the power I pi equal to cos pi plus I sin pi. This is equal to 0. This is equal to minus 1. So e to the power, beta being minus 1 means beta is equal to e to the power I pi, which is equal to e to the power 2 pi I gamma, which means gamma equal to pi by gamma equal to 1 by half. Gamma is equal to 1 by half. So your Flemmel's function now will become z plus a to the power minus half and z minus a to the power gamma minus 1, which is again equal to minus half. So this is half minus 1. This is again half. So this becomes 1 by root over z square minus a square. So that's your Flemmel's function for the second case. Remember, we have already proved that theta prime is 0. So what you are trying to do is omega prime, you are basically finding omega prime plus x plus omega prime minus x equal to p plus iq. That's what you're trying to find. So uh, so omega prime z will be this, with the xz being 1 by root over z square minus a square. Okay. Now with this Flemmel's function, we will have to evaluate this integral. We'll have to evaluate this integral, which is the main task here. Again, we can take pz to be equal to 0 for the same reasons that we cited for theta prime. Pz has to go to 0 as z tends to infinity, and that can only happen in case of polynomial if it's 0 everywhere. So this can be taken as 0. So the result is that you have to derive this integral, and if you do that, then you have the whole solution. Xz is given to you. Okay, so let's see how to derive this integral. In this integral, p plus iq is a constant, so we will be able to get away by evaluating this integral. This integral we will be able to evaluate, and to evaluate this, we have done integrals, principal values of integrals earlier when we were recapitulating our complex variable theory. And then many such integrals can be evaluated by actually evaluating a contour integral. So what we are going to do is, we are going to evaluate this contour integral. Zeta is a complex number. So x zeta, some zeta minus z. This contour integral we are going to evaluate, and the contour that we are going to take is a contour over c plus c naught, where c naught is this big circular contour whose radius r tends to infinity, and then c is a contour that just wraps around the crack. So these are very small circles whose radii go to 0. Then here you go along the crack from a to minus a. Here again there's a small circle whose radius goes to 0. Go along the crack from minus a to a. So here your xz has values x plus, and here your xz has values x minus. Okay, so these are the values of x plus and x minus. Remember that xz is the solution of the homogeneous Hilbert problem. So x plus x minus beta x minus x is equal to 0. So because xz is a solution to the homogeneous Hilbert problem, right? So now we will be able to evaluate this contour integral. Remember, we are going to evaluate the contour integral over c plus c naught 1 d zeta by x zeta minus z. This is the contour integral we are planning to evaluate. One more fact that I want to state here: if you evaluate this contour integral over this small circle and this small circle, when the radius of the circle tends to 0, this radius tends to 0, then the integrals give rise to 0. So this is a fact that I'm not going to prove. It's easily proved by taking radii along these kinds of circles for this function, which remember is 1 by root over zeta square minus a square. We have already derived that this is x zeta. Okay, this is the Flemmel's function. So we will accept these facts. So this is easy. Here it is x plus, here it is x minus. On this, the contour integral goes to 0. On this, the contour integral goes to 0. And this is a big circle whose radius tends to infinity. And x plus and x minus are related to each other through this homogeneous Hilbert problem. So with this, we will be able to now formulate the contour integral and derive, especially derive the integral from minus a to a. So this is the line integral that we are trying to derive, dx by x plus x into x minus z. This is the integral that we are trying to derive. We are actually trying to derive this integral on this line, but in order to do that, we are taking this whole contour integral because we have better tools to derive contour integrals, and we expect that part of this contour integral will be this integral, and I'll be able to get this in terms of the other terms. Okay, so we'll see how we can do that in the next module.